Okay, welcome back. Good evening. Just a second. Okay, welcome back. Good evening. வணக்கம். நல்லா இருக்கியா? Good evening. Namaskar. Okay, fine. Okay, what is the answer for this one? Everything is good and fine. What is the answer for this one? Any answers from your side? I have given it as an all. No. No one is correct. These are not regular questions. These are something typical questions. I have intentionally taken. There was no such questions in the exam so far, but to be at the safer side, we'll discuss all the varieties. Okay, fine. Observe this one. Given rho L is equal to 2x plus 4y, 3y plus minus 4z coulomb per meter. Find the charge on the line segment extending from 2, 1, 5 to 4, 3, 6. Clear? How do you find out the total charge beta? In the last session, what we have seen? Different types of charge distributions and corresponding electric field expression. For the line charge, line integral. For the surface charge, surface integral. For the volume charge, volume integral. Need to be performed. So we have seen in the last session, one question related to the volume charge. Here it is a line charge beta. So here is a solution. What is the line charge here? How do you find out the total charge from the line charge? Total charge is equal to rho L into DL. Yes or not? It is rho L into DL. But how do you find out this rho L? It is said that here you need to find out the magnitude of the differential length. Yes, see here. Extending from here to here. I'll write down that means here. Two x plus 3y minus 4z into DL. I'll find out the relation between all the things. Here it is said that from initial to final point. Yes. What is the line segment? How do you write down the line expression? X minus x1, x minus 2 divided by x2 minus x1, 4 minus 2. Y minus y1 is 1 divided by y2 minus y1, 3 minus 5. Z minus z1 divided by 6 minus 5. I'll call it as a some T or A or B, say. Okay, fine. And one more thing here, what is the range of t? Suppose if I substitute here in the place of, if I substitute the initial value of x, here it is 2. 2 minus 2 is 0. If you substitute the initial value here, that is 1. 1 minus 1 is 0. If I substitute 4 here, sorry, initial point is 5. 5 minus 5 is 0. That means the range of t is, initial point is 0 to, if I substitute the final point here, what is the final point is 4. 4 minus 2 by 4 minus 2, which is 1. You can check from here also. What is the final point is 3. 3 minus 1 by 3 minus 5. It is 2 by t. It is again 1. So the t range is from 0 to 1. Clear, beta? Okay. Now I'll convert everything, all the x, y, z into t. How can you do that one? X minus 2 by 4 minus 2 is equal to t. From here you can write x is equal to 2t plus 2. Y is equal to 2t plus 1. Z is equal to t plus 5. Clear? So what I'll do, I'll convert this entire row. I'll convert that entire row, that means line charge, into the variable t. What is this rho L beta here? Rho L is equal to 2x plus 3y minus 4z. So rho L is equal to 2 into x. What is x? 2t plus 2 plus 3 into y. What is y? 2t plus 1 minus 4 into t plus 5. So convert this one, how much you will going to get? Rho L is equal to 4t plus 4 plus 6t plus 3 minus 4t minus 15. So here rho L is equal to 6t. 6t how much is this? It is 20 beta. $60 minus 13. Okay, fine. So you have got a line charge in the single variable. Then I want to find out this differential length. Generally, what is the differential length? We know dl is equal to dx x cap plus dy y cap plus dz z cap. This can be written as dx by dt into dt x cap plus dy by dt into dt y cap plus dz by dt into dt z cap. Clear, beta? So what is this dx by dt? dx by dt is 2. dy by dt is 2. dz by dt is equal to 1. Let me turn the page here. So what happens to the dl beta? dl is equal to 2 into dt x cap plus 2 into dt y cap plus 1 into dt z cap. But we want a magnitude here. Magnitude can be written like this or modulus, which is equal to square root of 4 dt square plus 4 dt square plus dt square. So dl is equal to 3 into dt. So now you have got everything in a single variable. Just find out the total charge. Rho L into dl. What is rho L beta? This is rho L. -60 minus 13 into dl. What is dl? 3 into dt. Perform the integration here. 3 into 6t square by 2 minus 13 into 2. What is the range of the t we have got? 0 to 1. Yes. So the limits are from 0 to 1. Upper limit minus lower limit. 3 into 1 square minus 13 into 1. Three into 3 minus 13, which is 3 into minus 10, which is total charge is equal to minus 30 coulombs is the answer. Oh, y is minus 2t plus 1. Y value is minus 2t plus 1. So what should I do then? Let us make it as a plus. We'll do some small correction here. Actually, this is correct only. Here I should write 1. Here it is 4, 3, 6 beta. Clear? We'll take one more question. Okay, thank you. How limit got? How we got limit? Just substituting here. If I substitute the initial point 2, I'll get 0. If I substitute the final point, 4 minus 2 by 4 plus 2, 4 minus 2, it is 1. Let us take one more question, beta. Question on the surface charge. Find the total charge on the triangle of figure given surface charge density rho s is equal to 6 xy coulomb per meter square. So this is a part of the diagram, part of the question, this diagram. This is a figure shown. Here it is 1, here it is 2, here it is 3, here it is 1, here it is 2, here it is 3, here it is x, here it is y. So you need to find out what is the charge on this one. Surface charge is given, you need to find out the total charge. Then what should I do? Integration. What kind of integration is this? It is a surface integral I should perform. Yes, beta. What is the surface integral? Q is equal to surface integral of rho s into dA. But you need to choose the limits properly here. What is the x limits? X limits are from 1 to 2. But if I take the y limits from 1 to 3, this will going to give the rectangle, but not triangle. Clear? Yes. So what should I choose here? I should choose the x limits from here to here, but y limits from here to here. So that I can cover this entire this. Clear, beta? Yes. So how I can choose the limits here? Here it is. What is this point? This point is 2, 1. What is this point? 1, 3. What is the y value here? Somewhere here. That means you need to find out the expression. Isn't it? Line expression. So what is the line expression, beta? So I'll choose the x limits from 1 to 2. Y limits, it is like this. If you consider the strip like this. Like this. So that I can cover the entire that area. Clear? Yes. So I should find out the y value somewhere here. How do you find out the y value? Straight line equation, isn't it? It is the initial point, this is the final point. Yes. What happens, beta? X minus x1 is 1 divided by x2 minus x1 divided by y minus y1 is y minus 3 divided by y2 minus y1. So here it is x minus 1 is equal to y minus 3 by minus 2. Bring that one there. So here it is minus 2x plus 4 is equal to y minus 3. Y is equal to minus 2x plus 7. Sorry, here it is 2. Plus 5. So here is a y value is minus 2x plus 5. Clear? So you need to take the y value from where? Y value from 3 to here. X value from 1 to here. And you need to integrate this one so that I can cover this one. Yo, hope you would have learned all these things in your mathematics. Just it is a recapitulation. So here, charge Q is equal to, it is in the XY plane. Differential area is dx to dy. Surface integral of 6xy yes, y limits are from, y is from 3 to minus 2x plus 5. X limits are from 1 to 2. Here it is 6 xy dy dx or dx dy. First, I'll going to integrate with respect to y. Yes. So I'll going to integrate like this. Later, I'll going to change the x value so that I can cover that entire triangle. Clear? Yes. So here it is. X is from 1 to 2. 6x y square by 2. Limits are from y is equal to 3 to minus 2 plus 1 into dx. Substitute upper limit minus lower limit. I'll going to turn the page. X is from 1 to 2. You can bring the 6 outside. X into minus 2x cap. You can bring the 2 also outside, 1 by 2. Minus 2x plus 5 whole square. Minus 3 square into dx. Expand this one beta. 3 into x is from 1 to 2. 4x square plus 25 minus 20x minus 9 into dx. So how much you will going to get? A small correction here. What is y? Yes, y is from, yes. So how much you will going to get? Speak out. 3 into I'll repeat the limits. So how much you will going to get this one? 4x cap minus 20x plus 16 into dx. 3 into 4x cube by 3 minus 20x square by 2 plus 16x. Limits are from 1 to 2. Upper limit minus lower limit. 3 into 4 by 3 into 8 minus 20 into 2 square is 4 by 2. Here it is 2 square by 2 plus 16 into 2 minus 4 by 3 1 cube minus 20 into 1 square by 2 plus 16 into 1. So how much is that? Please check out. Oh, here there is a x. The x is missing here. Just a minute. Yes, there is x is there. 3 into x is from 1 to 2. X 4x square minus 20 x plus 25 minus 9 into dx. 3 into x is from 1 to 2. 4x cube minus 20x square plus 16x into dx. 3 into 4x to the power of 4 by 4 minus 20 x cube by 3 plus 16 x square by 2. Limits are from 1 to 2. Upper limit minus lower limit. 3 into 2 to the power of 4 minus 20 by 3 into 2 cube plus 8 into 2 square minus 1 to the power of 4 plus 20 by 3 into 1 cube plus 8 into 1 square. Give me the answer. How much is this? Yes, how much is this? Is it clear? So how much is that? Check out. 23 or minus 23? Minus 23 you're going to get. Let me repeat one more time. Some of your friends are facing difficulty in choosing the limits. See here, I cannot simply take the limits. X is from 1 to 3 and y is from 1 to 2 and y is from 1 to 3. If I take like that, it will going to make a rectangle. It is not a rectangle, it is a triangle. Okay. So here, I need to consider the small piece of this one here. Small strip here. And if I add one more strip here, and if I add one more strip here, and if I add one more strip here, that will going to cover the triangle. So what are the strip limits? Strip limits are from here to here. That is the y limits. X limits are from here to here. Yes or not? Some arbitrary point. What is the arbitrary point? It from the straight line expression you have got a y. So the y value is starting from 3 up to somewhere here. X limits are from starting from 1 to somewhere here. If you take the overall limits, here to here, y limits. X limits are from here to here. I'll take it for the strip. Yes, that is the thing. Is it clear now? Is it clear now? So if I place strip after the strip, I can cover the triangle. Okay, hope you have got this one. Fine. So I've intentionally taken some typical questions here. There was no such question so far, but to be at the safer side. Any problem in deciding the limits? That is the crucial point in your mathematics also, isn't it? When you are dealing with the integrals. deciding the limits. Any doubts? Okay, fine. Let me go back here. Now, yesterday we have seen different types of charge distributions. Infinite line charge, infinite sheet charge. Sorry, a line charge, sheet charge, isn't it? Here, remember, there are two formulas are important for our exam. One is electric field due to infinite uniform line charge. Other one is electric field due to infinite uniform sheet charge. Substitution kind of questions are expected. Let me turn the page here. So we're going to see the two formulas here. Electric field due to infinite uniform line charge. Royal units are coulomb per meter. Here we will not going to do any derivation, which is not required for our exam, GATE and as well as engineering services prelims. Here is an infinite uniform line charge. Which is extending from minus infinite to plus infinite. Here it is the Z axis. What is the charge on this one? The charge on this one is Royal. Coulomb per meter. Okay. So I am orienting. I'm going to use what is called a cylindrical coordinate system. This is an infinite line charge. I am placing for the on the Z axis. The electric field is radially outwards. Electric field is in which direction, beta? Radially outwards direction. Okay. I want to find out the electric field somewhere here. That electric field will going to depend on the distance from here to here. Distance from here to here is a rho. Okay. And electric field here is a radially outwards. It is E rho. Radially outwards in all directions. Okay. See here. What is the form? What is the expression need to be used to find out this electric field, beta? Electric field E is equal to line integral of rho L into dA divided by 4 pi epsilon r square into r cap. I will not going to do any derivation. No, no derivation. Derivations are not required for us. Clear? So directly after substituting the limits from minus infinite to plus infinite, after the very lengthy derivation, you will going to get a formula like this. The formula for this one is E is equal to rho L by E is equal to rho L by 2 pi epsilon rho into rho cap. This is the formula need to be remembered. Clear? Yes. So in which direction this electric field is? Let us make some observations here. The electric field is in the radial direction. And what is this rho? It is a perpendicular distance. That means electric field due to infinite uniform line charge is inverse proportional to the perpendicular distance, and it is in the radial direction. Clear? Yes. Now let us take some examples here to understand this one further. I'll going to turn the page. So here is the electric field. E is equal to rho L by 2 pi epsilon rho into rho cap. How the electric field? Try to understand this one. Here is the infinite line charge is there with us. Let us consider this one. This is the infinite line charge beta. So how the electric field is? Radially outwards from all sides. Radially outwards. Radially outwards. And it is inversely proportional to the perpendicular distance. This is a formula. Need to be remembered. But let us try to have some understanding of this formula properly. So here is a infinite line charge beta. Which is extending from minus infinite to plus infinite. What is the charge on this one? Is a line charge. Rho coulomb per meter. I want to find out the electric field at the different instants. I want to find out the electric field here. I want to find out the electric field here. I want to find out the electric field here. Okay. What happens to the electric field at the first point? At any point, it is radially outwards. Clear? But the electric field there is dependent on the perpendicular distance. Which distance it is? It is on the perpendicular distance from here to here. So what is the electric field there? I'll call it as a E1. E1 is equal to rho L by 2 pi epsilon rho 1 into rho 1 cap. So here it is a rho 1 vector. Perpendicular distance vector beta. Then what about the electric field here? That is also radially outwards. But that is dependent on the perpendicular distance from there, from the charge to that point. It is like this. So here it is a perpendicular distance beta. The perpendicular distance here is, here it is a rho 2 vector. So what is this E2? E2 is equal to rho L by 2 pi epsilon rho 2 into rho 2 vector. Clear beta? Observe here. What is the electric field at this point? Radially outwards. Clear? Yes. So here it is the radially outward direction. So it is dependent on the perpendicular distance. What is the perpendicular distance? Let us say it is a rho 3 vector, which is equal to E3 is equal to rho L by 2 pi epsilon rho 3 into rho 3 cap. So we'll going to follow some terminology here. I'm going to call this as a SP, source point. I'm going to call this as a FP, field point. Here it is field point, here it is source point. Here it is source point. Here it is field point. What is the source point? What is the field point? Where you want to find out the electric field is a field point. What is the source point beta? If I drop a perpendicular onto the line charge, wherever it intersect, that is a source point. Yes. So what is the SP here? We will going to follow this terminology. SP is source point. What is FP? Is field point. So here is a perpendicular. Electric field is acting from source point to the field point. And rho is a perpendicular distance vector. Clear? Okay, fine beta. Let me turn the page here. This is all about the electric field due to infinite uniform line charge. Now let us try to find out one more. Let us try to understand one more formula. I'll going to turn the page. Electric field due to infinite uniform sheet charge. Here it is rho s. Units are coulomb per meter square. Okay, fine. Now observe here carefully. Let us consider the infinite sheet beta like this. Here it is the infinite sheet. It is extending to positive infinite here, negative infinite here, positive infinite here, negative infinite here. What is the charge on this one? It is a surface charge, rho s. Units are coulomb per meter square. Clear? I want to find out electric field at certain distance from this infinite sheet. At certain distance from this one. Somewhere here. So the electric field here is outwards. You should call this as a normally outwards. We cannot call it as a radially outwards. You can call radially outwards for the line charge. Yes. So here it is a sheet like this. It is a sheet charge like this. So it is an infinite extent. If it is an infinite extent, you cannot see its corners, isn't it? So the electric field only from the two sides. Here it is outside like this, if it is positively charged, and here also it is outside. So the electric field exists only on the two sides. So you should call it as a normally outwards, not radially outwards. Radially outwards when it is the line charge. The electric field is like this, like this, like this, like this, and so on. Clear? Yes. Then how do you find out the electric field here? Using that expression what I have given. E is equal to surface integral of rho s into dA divided by 4 pi epsilon r square into r cap. Clear? If you perform the integration and all the story, I will not going to do any derivation here, which is not required for us. You will going to get E is equal to rho s by 2 epsilon plus or minus n cap. This is the electric field. Electric field is normally outwards from the two sides of the sheet, and it is independent of distance. Yes. Okay. So what it is here, it is independent of distance. Independent of distance. And which direction it is? It is in the normal direction. To have the further visualization, let me turn the page here. I'll going to draw what is the electric field here. E is equal to rho s by 2 epsilon plus or minus n cap. I'll going to draw the infinite sheet like this. Which is extending from minus infinite to plus infinite. If I put a line and if I put a dots here, what does that indicate? It indicates the sheet. If I draw a line, what does that indicate? Just indicates the line. But if I draw a line, if I put a dots here, what does that indicate? It indicates the sheet like this. You are seeing the sheet like this. So if you see the sheet like this, what you'll notice? You'll notice the line. Yes. So that is the meaning of that. And what is the charge on this one? Rho s units are coulomb per meter square. I want to find out the electric field here. I want to find out the electric field here. I want to find out the electric field here. Let us take this as a plus or minus n cap. This will become minus or plus n cap. Clear? Yes. So what happens to the electric field here? It does not depend on the any distance, isn't it? The only thing is electric field is normally outwards. So what is the electric field? E1 here, let me call, is equal to rho s by 2 epsilon plus or minus n cap. What about this one? Here it is normally outwards. E2 is equal to rho s by 2 epsilon plus or minus n cap. This side beta normally outwards like this. I'll call it as a E3. E3 is equal to rho s by 2 epsilon minus or plus n cap. Clear? Yes. So this is all the story. These are the two formulas. Repeatedly, there was questions were noticed from these formulas. Try to remember these two formulas. Now let us try to have the varieties of questions on these formulas. Let us start with the question here. An infinite uniform line charge of density 10 nanocoulomb per meter is located at x is equal to 3 meters, comma, y is equal to 4 meters. And parallel to z. Find electric field due to this infinite line at following points. Question A 0, 0, 0. Question B 4, 5, 6. Question C 8, 8, 8. Yes. You need to draw some diagram here. Without diagram, you cannot solve this question. Yes. Okay. Let us try to draw some diagram here. Where is this infinite line charge is located, beta? Let us draw the coordinate system. Here is the x-axis. Here is the y-axis. Here is the z-axis. Where this infinite line charge is located, x is equal to 3. 1, 2, 3. Y is equal to 4. 1, 2, 3, 4. And parallel to z-axis. Let us make some box out of this for the 3D visualization. So where this infinite line charge is located, x is equal to 3 meters, y is equal to 4 meters and parallel to z-axis. So here this is how located. Yes, beta. And what is the charge on this one? The charge on this one is given as Royal nanocoulomb per meter. What is this point? This point is in the XY plane. So here it is 3, 4, 0. What is this point? 3, 4, some Z. 3, 4, Z beta. So what is changing on the line? Z value is changing, isn't it? Yes or not? X and Y values are fixed. Listen carefully. Observe here. How do you find out the electric field due to this infinite line charge? E is equal to rho L by 2 pi epsilon naught into rho cap. Sorry. 2 pi epsilon naught into rho cap. What is this unit vector can be written? Vector by its magnitude, which is rho L by 2 pi epsilon naught vector by its magnitude square. Yes, in place of if you substitute unit vector. That means to find out the electric field, you need a perpendicular distance. Yes, observe here carefully. How do you find out the perpendicular distance from the field point? What is the field point? From the point where you want to find out the electric field. Now I'm going to show some example here. Here it is, let us say some point 8, 8, 8. 8, 8, 8. I'll drop a perpendicular onto this one. What happens to this point? My claim here is this is a perpendicular distance vector. Here it is a row vector. So what I am claiming here, it is a perpendicular distance. So what happens to this point? This point is on that point, 3 and 4 are fixed. X and Y values are fixed. 3, 4, Z. What will be the Z value? If my claim has to be correct, what should be the Z value there? It should, for it to become a perpendicular distance. Come on, speak out. I want answers from your side. What must be the Z direction? What must be the Z value? I want answers from your side. Z value must be 8. Very good. Very good. Here the Z value must be 8. Then only these 2 points will correspond to the perpendicular distance. If the Z value is different, that is not a perpendicular distance. Yes or not? Okay. So here Z value must be same. And in our terminology, what you are calling this, you are calling it as a field point. And this we are calling it as a source point. Clear? Fine. Let me turn the page here. First part of the question, beta. What is the field point? 0, 0, 0. At 0, 0, 0, I want to find out the electric field. So what is the source point? 3, 4, Z. To get a perpendicular distance from here to here, I'll call it as a rho 1. I should maintain the same Z value. I should maintain the same Z value. Clear? Yes. So what happens to this one? Here it is. E1 is equal to rho L by 2 pi epsilon naught rho 1 vector by rho 1 square. So the E1 is equal to, what is this rho 1 beta? What is this rho 1? Rho L value is 10 nano. So here it is 10 into 10 to the power of minus 9 divided by 2 pi into 1 by 36 pi into 10 to the power of 9 into rho 1. What is rho 1? 0 minus 3. It is minus 3x cap. 0 minus 4. Here it is minus 4 y cap divided by its magnitude is 9 plus 16 whole square. So here it will become 18. If you take into the numerator, this will become E1 is equal to 180 divided by 20 pi minus 3x cap minus 4y cap. Clear? Yes. Units are Newton per Coulomb. Similarly, what you can do, you can find out second part of the question. What happens for the second part of the question? Four, 5, 6. What is the field point beta? 4, 5, 6. What is the source point? 3, 4, Z beta. To get a perpendicular distance, what should I do? I should maintain the same Z value. Yes or not? That means I should maintain, to get a perpendicular distance, I should maintain the same Z value. Here it is 6. Here it is rho 2 vector. What is this E2? E2 is equal to rho L by 2 pi epsilon naught rho 2 vector by its magnitude square, which is equal to E2 is equal to 10 into 10 to the power of minus 9 divided by 2 pi into 1 by 36 pi into 10 to the power of 9. 4 minus 3, it is x cap. 5 minus 4, it is plus y cap. Divided by its magnitude is square root of 1 plus 1 whole square. So the E2 is equal to 180 divided by 2 x cap plus y cap. Clear, beta? What is the third part of the question? Let us try to address that. I'm going to turn the page here. What is the third part of the question? What is the field point? 8, 8, 8. 8, 8, 8. What is the source point? 3, 4, Z. I need a perpendicular distance. I'll call it as a row 3 vector. To get a perpendicular distance, I must maintain the same Z value. So what is this E3? E3 is equal to rho L by 2 pi epsilon naught. Rho 3 vector by its magnitude square. Just substitute all the values. 10 into 10 to the power of minus 9 divided by 2 pi into 1 by 36 pi into 10 to the power of 9 into 8 minus 3 is 5x cap. 8 minus 4 is plus 4y cap. Divided by square root of 25 plus 16 whole square, which is E3 is equal to 180 divided by 41 x cap plus 4y cap. Clear, beta? See here, if you go back and see, this is what I have taken as an example, isn't it? I'm taking a point 8, 8, 8. So here it is 3, 4, 8. This I have taken as an example to explain the concept of perpendicular distance. Clear? We'll take one more question. So by maintaining the Z, because here the infinite line is parallel to the Z, that is the reason why we need to maintain the same Z value. In other problem, the infinite line may be parallel to the x-axis, parallel to the y-axis. Depending on that, you need to take. Okay. Let us take one more question, beta. I'm going to turn the page. An infinitely long uniform charge of density. An infinitely long uniform charge of density 30 nanocoulomb per meter is located at y is equal to 3 meters, comma, z is equal to y meters, and parallel to x. The field intensity at 0, 6, 2 is 0, 6, 2 is E is equal to 64.7 y cap minus 86.3 z cap volt per meter. What is the field intensity at 5, 6, 2? Options are given. Option A is E. Option B is 6 square plus 1 square divided by 6 square plus 1 square to the power of 1 by 2 into E. Option C, 6 square plus 1 square divided by 6 square plus 5 square plus 1 square into E. Option D. Six square plus 5 square plus 1 square divided by 6 square plus 1 square into E. Yes, come on, what is answer? What is the answer for this? Epsilon value, if it is not specified, you have to take it for the air. For the air, epsilon is equal to epsilon naught. Okay. So what is the answer for this? First, let us try to understand the question properly. An infinitely long uniform charge of density, how much? 30 nanocoulomb per meter is located at y is equal to 3, z is equal to 5, parallel to x-axis. Okay. So what is varying here? X value is changing. Y and z are fixed. The field intensity at 0, 6, 2 is given. Is this one. What is the field intensity at 5, 6, 2? Okay, fine. See here, how do you find out the electric field intensity beta? Due to infinite line charge, E is equal to rho L by 2 pi epsilon rho into rho cap. Rho is equal to vector by its magnitude. E is equal to rho L by 2 pi epsilon vector by its magnitude beta. Magnitude square. Okay, let me finish the question here itself. Where the electric field is given? The electric field is given at 0, 6, 2. Yes. So what is the field point he has given? The field point, or let me turn the page here. I'm going to turn the page here. Where the field point is given? 0, 6, 2. What is its corresponding source point? Here the infinite line is parallel to the x-axis. Y and z values are fixed. Here it is x, let me go back, 3, 5. To get a perpendicular distance, I'll call it as a rho 1 vector. I should maintain the same x value here. So what happens to the perpendicular vector? Rho 1 vector here is equal to 0 minus 0, 0, 6 minus 3, it is 3y cap, 2 minus 5, it is minus 3z cap. 6 minus 3, it is? Yes. 6 minus 3, it is 3 y cap. 2 minus 5, it is minus 3 z cap. This is a perpendicular vector. And it is given that we know that E1 is equal to rho L by 2 pi epsilon naught. Rho 1 vector by its magnitude square. It is given as a E. It is given as a E already. Yes. So what question is asking? Is asking at some particular point. Which one? 5 comma 6 comma 2 beta. 5 comma 6 comma 2. At what point is asking 5 comma 6 comma 2? What is the source point? X comma 3 comma 5. Am I correct? Yes. So to get a perpendicular distance, rho to vector, I should maintain the same x value. Yes. So what happens to the rho to vector here? Rho to vector is x 5 minus 5 is 0. 6 minus 3 it is 3 y cap. 2 minus 5 is minus 3 z cap. So what is E2 beta? E2 is equal to rho L by 2 pi epsilon naught rho 2 vector by rho 2 vector magnitude square. Are here rho 1 is equal to rho 2 beta. Rho 2 is equal to rho 1 vector. That means E2 is equal to E1, which is equal to E. So the for this question, this one for a given thing and for the new thing, perpendicular vector is same, isn't it? Anyhow, this is constant. This is same here and here. So at the new point also, electric field will be same. So what is the answer? Let me go back. Option A is the answer. Clear? Let us take one more question, beta. Are you with me? Are you following? Yes or no? Say something. Okay, let us take one more question, beta. Figure shows kite, K-I-T-E, kite shape in the figure shows the kite shape in the XY plane having line charges parallel to Z axis through 3 of its corners. Through 3 of its corners. Find electric field at the 4th corner. This is a diagram provided in the question. I'm going to draw. Here it is x-axis, here it is y-axis. Z-axis is outside the board. Here it is minus royal, minus 2 royal. Here it is royal. Here it is royal. These two are perpendicular. These two are perpendicular. This is angle theta. This is angle theta. This one is B length. This one length is A. This is A. This one is B. And this one is C. Yes. Come on, speak out. Try to understand the questions properly first. Figure shows the kite shape. These infinite line charges are arranged like a kite. In the XY plane, having the line charges parallel to the Z axis. Okay. Through the three corners, through three of its corners. Find the electric field at the fourth corner. See here, the royal is like this. Royal is like this, one more royal. Here it is minus 2 royal is. They are parallel to the Z axis. I want to find out the electric field at the fourth corner beta. Means here. What happens to the electric field there? Little bit vector approach you need to follow. Little bit vector approach you need to follow. Yes, how do you do that? What we know, the electric field is, how the electric field is beta? Electric field is rho L by 2 pi epsilon rho cap. What is the electric field due to this charge? Here I want to find out. Here it is radially outwards. Here it is radially outwards. Here it is radially inside because it is negatively charged. Yes. So I want to find out here beta. So I'm going to follow the vector approach here. Observe this one carefully. What is the electric field due to this one at this point? Radially outwards. Let me give some naming for this one. I'll call it as the first charge. This is the second charge. This is the third charge. I'll call it as a E1 beta. What is the electric field here beta? What is the electric field here due to this one? Radially outwards. Means like this. This is E2 beta. Yes. What is the electric field here due to this one? That is radially inside because it is negatively charged. Clear? This is E3 beta. What is the magnitude of E1? Only magnitude of E1. Magnitude of E1 is equal to magnitude of E2. Why like that? Why? Because Distance from here to here and here to here are same. Clear, beta? Yes. So what it is here? It is rho L by 2 pi epsilon into what is the perpendicular distance is B. Now resolve into the components, beta. This angle is theta. I'm showing all the things onto the same diagram. This angle is also theta. This angle is also theta. This is theta. This is also theta. Resolve into the components. Like this. Like this. And like this. So what happens to this one? Here it is. This one is E2 sin theta. Here it is E1 sin theta. Here it is E2 cos theta. Here it is E1 cos theta. Clear, beta? So this one and this one will cancel out. This is in the positive y direction and this is in the negative y direction. So at the fourth corner, there will be only three components. One is E3, other one is E2 cos theta, E1 cos theta. E1 magnitude is equal to E2. That is the reason why this one and this one will cancel out. Clear? Yes. So what is the total electric field at that point? E total. And one more thing. Let us write E3 here. Only the magnitude of E3 is 2 rho L by 2 pi epsilon into what is the distance from here to here is C. Okay. Then what is the total electric field at that fourth corner is this component, and then this component. So here it is E1 cos theta x cap plus E2 cos theta x cap plus E3. Which direction is that? Negative x direction. Negative x cap. E1 is equal to E2 beta. This can be written as E2 into E1 cos theta x cap minus E3 into x cap. What is the cos theta beta? Let me turn the page here. What is cos theta? You can look at from here. Cos theta here is a right angle triangle. Adjacent by hypotenuse B by C. Cos theta is B by C. So just substitute all the values properly there. What is this E total? E total is equal to 2 into E1. What is E1? Rho L by 2 pi epsilon B into x cap minus E2. What is, sorry, E3. What is E3 beta? 2 rho L. Just a minute, we forgot this cos theta. What is the cos theta? B by C. X cap minus E3 beta. What is E3? 2 rho L by 2 rho L divided by 2 pi epsilon into C x cap. So what is this E total? 2 rho L. This B will cancel out. So here it is 2 pi epsilon into C x cap minus 2 rho L divided by 2 pi epsilon into C x cap. So here E total is equal to 0. That is the story. Clear? Let us have one more question, beta. I'll going to turn the page here. Three infinitely long charged lines run parallel to the z-axis as shown in the figure. The lines have uniform charge densities as shown. Determine the electric field at P. So these are diagrams shown, beta. Here it is minus rho L coulomb per meter, rho L coulomb per meter. Yes, and here it is. The distance from here to here it is A. And the distance from here to here also A. Clear? And it is mentioned that here it is minus rho L coulomb per meter. Here it is x-axis. Here is a point P. And the distance from here to here is B. And the distance from here to here is not given. Here is a point P. And this angle is theta. Here z-axis is outside the board. Here also same story. Use the vector approach. Here three charges are how they are? They are running parallel to each other. Any answers from your side? Let me redraw the diagram in the next page for clarity. Okay, let me turn the page here, beta. This is the diagram. Minus Royal Coulomb per meter. Royal Coulomb per meter. Minus Royal Coulomb per meter. Here is a point. Here it is B. Here it is A. Here it is A. Yes. Okay. What is the distance from here to here, beta? So here is a point P. At this point, you need to find out. Here it is the z-axis provided. Here it is the x-axis. So obviously, this point will become what? This will become y-axis. Yes, x cross y is z outside the board. Clear? Yes. Observe here, beta. These are negatively charged. What is the electric field due to these things? We know that. Let me give some naming for them. I'll call this as a 1. This as a 2. This as a 3, beta. Clear? So apply the vector approach here also. What is electric field? E is equal to rho L by 2 pi epsilon rho cap. 3 lines are there running parallel to the z-axis. Okay. So what happens here? Electric field due to this one, it is a negatively charged one. So the electric field is towards that one. Here also this is negatively charged towards this one. Here it is E1, here it is E2. What is this angle, beta? This angle is theta. That is what mentioned already. Here it is radially outwards due to E3. I'll go to resolve into the components. Here, I just write down the magnitude of E1. Magnitude of E1 is equal to E2. Why? Because what is this length, beta? Square root of A square plus B square. Here it is square root of A square plus B square, beta. Clear? So here it is. What is this E1? E1 is equal to E2 is equal to rho L by, I'm writing only the magnitude. 2 pi epsilon into what is the distance, beta? Square root of A square plus B square. I'll go into, and what is this E3 then? E3 magnitude is rho L by 2 pi epsilon into B, beta. I'll go into resolve into the components like this, like this, like this. Like this. Yes, beta. So what happens to this one? Here it is E1 cos theta. Here E2 cos theta. Here is E2 sin theta. Here it is E1 sin theta. Yes. So what happens to this one is this one and this one will cancel out. So what is the overall electric field at the point P is equal to E1 cos theta in the negative y direction plus E2 cos theta in the negative y direction plus E3 in the y direction beta, positive y direction. Bas khatam. How this can be written further in a simplified fashion? E1 is equal to E2 beta. So here it is 2 into E1 into cos theta minus y cap plus E3 into y cap. So what is the cos theta here? Let me turn the page. What is the cos theta beta? Let me go back. Here is this is a right angle triangle. Adjacent by hypotenuse. B by square root of A square plus B square. Okay, beta. Just substitute there. So here it is. EP is equal to, let me go back. 2 into E1. What is E1 beta? Rho L by 2 pi epsilon square root of A square plus B square into cos theta. What is cos theta? B by square root of A square plus B square into minus y cap plus E2, E3. What is E3? Rho L by 2 pi epsilon into B into y cap. Kata. So E total is equal to 2 into rho L into B divided by 2 pi epsilon into A square plus B square minus y cap plus rho L by 2 pi epsilon into B y cap. Further, if you can simplify according to the options. 2 pi epsilon into y cap 1 minus 2 divided by it is by B. Here it is 2B divided by A square plus B square. Clear? Further? Rho L by 2 pi epsilon y cap A square plus B square minus 2B square divided by B into A square plus B square. Rho L by 2 pi epsilon into y cap A square minus B square divided by B into A square plus B square. Clear? So this is the answer. Let us have one more question. Why we resolved the fields? See here, no doubt point P is a point, but here the electric field is acting there. Electric fields are making angle with each other. Okay, fine. Let us proceed further. Let us have one more question. I'll going to turn the page. All these are varieties of questions on the infinite line charge beta. Now let us take the questions on infinite sheet charge. Infinite sheet charge questions are very simple because electric field due to infinite sheet charge is independent of distance. Here you need to identify only a normal direction. Okay, let us have a question here. Infinite uniform surface charge of 1 by pi nanocoulomb per meter square is located on Z is equal to 6 meters plane. Find electric field at following points. Question A 0, 0, 0. Question B 10, 10, 10. Question C 20, 20, minus 20. Yes, it is a very straightforward formula. Here you no need to decide anything regarding anything like a perpendicular distance. Okay, fine. Now let us focus here. Where this infinite sheet is located, beta? Z is equal to 6 meters plane. Let us draw the coordinate system like this. Here it is x-axis, here it is y-axis, here it is z-axis. So where this infinite sheet is located, Z is equal to constant plane. Yes, so it is like this. Z is equal to constant plane like this. Yes, fine. It is like this. Let me use some other color. So where it is, beta? Z is equal to 6 meters plane. Okay, and what is the charge on this one? Is rho s nanocoulomb per meter square. Clear, beta? And how the normal is for this one? If it is fixed at Z is equal to constant plane, The normal is outwards, isn't it? So here it is like this. The normal here is Z cap. Below it is minus Z cap. What is the electric field expression beta? Due to the infinite sheet, E is equal to rho S by 2 epsilon naught plus or minus N cap. It's a very simple formula compared to the earlier formula. Yes, beta. So here it is. Just substitute the values properly. E is equal to 1 by pi into 10 to the power of minus 9 divided by 2 into 1 by 36 pi into 10 to the power of 9 into what is the normal to the infinite sheet plus or minus Z cap. E is equal to, how much is this? You will going to get 18 plus or minus Z cap Newton per coulomb. At what point is asking beta? Let me complete here itself. At 0, 0, 0. What happens at 0, 0, 0? Come on, speak out. This point is it below the sheet or above the sheet? 0, 0, 0 is below the sheet. This point is somewhere here. Below the sheet. If it is below the sheet, what is the electric field direction? Minus Z direction. So the electric field E is equal to 18 minus Z cap. Next one, beta. Next point. Where is that point? 10, 10, 10 beta. Is it below the sheet or above the sheet? 10, 10, 10 beta. It is above the sheet. If it is a point is above the sheet, what is the electric field direction? It is in the positive Z direction. 10. Sheet is located at 6. So the electric field E is equal to 18 Z cap. Last one. Point C. 20, 20, minus 20. Is it below the sheet or above the sheet? 20, 20, minus 20. That is below the sheet, beta. If it is below the sheet, how can you notice from here? So the electric field is in the negative Z direction. That is the story. Clear? Yes. Very simple formula. The only thing is you should decide which is normal. Okay. Let us have one more question on this infinite sheet. An infinite uniform sheet charge of density 10 nanocoulomb per meter square is placed on on plane described by 2x plus 3y plus 4z is equal to 12. Find electric field on both sides of sheet. Think about this one. We'll go to the break now. It is the appropriate time to go for a break. After break, we'll solve this question, followed by the flux and magnetic field and Gauss law concept. We'll continue after the break, 20 minutes break. Okay, welcome back. Now let us try to solve this question here. An infinite uniform sheet of charge of density. How much is that? 10 nanocoulomb per meter square is placed on the plane described by, this is the plane. Find the electric field on the both sides. Earlier, our infinite uniform sheet charge was placed on Z is equal to constant plane, isn't it? But here it is some arbitrary plane. Let us try to plot that one. Here it is a here it is the x-axis, y-axis, z-axis. Where this infinite sheet is located, how do you plot this one? So to plot this one, what I'll do, I have to find out the x coordinate. I'll make y and z0. If I make y0, z0, what is the x? X is equal to 6, somewhere here. 1, 2, 3, 4, 5, 6. Here, to get the direction of, to get the coordinate of y, I should make these two things 0. So y is equal to 4. 1, 2, 3, 4. To get the value of z, I should make these two things 0. So z is equal to 3. Yes. 1, 2, 3. So here, let me draw this one in the first octant beta. Here is a thing like this. So this is a plane. That is how the infinite sheet is placed. Yes. How it is placed? It is placed with some inclination. It is something like this. Let me show you. In the earlier problem, the sheet was placed like this. But here, in the earlier problem, the sheet was parallel to the XY plane. But here it is something tilted like this. Fine. Whatever it may be, the electric field would be whether the sheet is like this or like this or like this or like this, doesn't matter. The electric field which is associated with the infinite sheet will be in the normal direction, normally outwards. The only thing is here we need to find out its normal direction. Yes, normal to the sheet. Remember, this is the infinite sheet. What is normal to this one? Normal to this one is something like this. It is normal like this. How do you find out the normal to the surface? What is the mathematical operator I should use? Come on, speak out. I have given that one already. How do you find out the normal to the surface? I want answers from your side. Gradient. Very good. Very good. It is a gradient. The direction of the gradient is nothing but a normal direction. Very good. Yes. So here it is. You can go back and check out the gradient concept, which I have explained in the very first class. Yes. So what is the gradient here? Let normal direction is gradient by its magnitude. Let I'll consider some scalar field as f is equal to 2x plus 3y plus 4z. I'll find out the gradient of f. What is the gradient of f? 2x cap plus 3y cap plus 4z cap. Yes or not? This is a gradient. So take its normal. 2x cap plus 3y cap plus 4z cap divided by its magnitude is 4 plus 9 plus 16, which is 2x cap plus 3y cap plus 4z cap divided by square root of 29. So this is a normal. This side, increasing side. What is the other side? Other side will be, that means other side of this one is minus n cap. Clear, beta? Let me turn the page here. So once you have got a normal, just it is a substitution. What is the electric field formula? E is equal to rho s by 2 epsilon naught plus or minus n cap. So here it is. What is this rho s? 10 nano beta. 10 into 10 to the power of minus 9 divided by 2 into 1 by 36 pi into 10 to the power of 9 into plus or minus n cap. So here it is. How much is this? 180 pi into plus or minus n cap. What is the electric field towards the origin side? It is minus n cap, isn't it? At origin side, E is equal to 180 into pi minus n cap. Let me go back. The origin side is other side beta, minus, isn't it? The infinite sheet is there like this. Here it is the normal, other side it is not like this. Okay. So which is E is equal to minus 180 pi into what is that normal? 2x cap plus 3y cap plus 4z cap divided by square root of 29. What is the electric field other than normal side, other than origin side? Other than origin. At other than origin. E is equal to 180 pi into plus n cap. So the E is equal to, it is plus, that's it. 180 pi into 2x cap plus 3y cap plus 4z cap divided by square root of 29. I leave the calculation part to you, remaining part to you. Clear, beta? Fine. So these are the some of the varieties of questions on the formulas what I have shown. Now let us go to the new concept here. I'll going to turn the page. I'll going to introduce the concept of what is called electric flux. Electric flux is represented with the symbol psi e. Units are coulombs. And electric flux density. It is represented by the symbol D. Units are coulomb per meter square. What is the concept of flux? I've explained that one during the surface integral. Okay, see here. Now let us consider what is called a charge distribution. What is a charge distribution? It can be a, when I say charge distribution, it can be a point charge, line charge, surface charge, volume charge, whatever it may be. It may be a point charge. It may be a line charge. It may be a surface charge, or it may be a volume charge, or combination of any of that. Okay. So if I have a charge here like this, what is there around this one? There are electric field lines are there. Now what I'll do, I'll place some surface here, open surface. What kind of surface is this? Open surface. So the field lines are entering from here, leaving from here. Field lines are entering from here, leaving from here. Field lines are entering from here, leaving from here. So I want to find out, that is nothing but a flux, isn't it? The amount of vector field crossing the given surface is nothing but a flux, isn't it? Now let us consider a small piece of area here. The area is dA. Okay. And here I'll consider the normal direction like this. The amount of vector field crossing through that small piece of area is called flux density. Flux crossing through small piece of area. Fine. So I'm going to represent that one with a D. Its units are coulomb per meter square, because this is per meter. So the amount of first step number one, the amount of vector field, especially what is field here? Electric field. The amount of electric field crossing the given surface is called a flux. And it is crossing the small piece of surface is called flux density. Clear? Yes. Now observe carefully. Let us define mathematically. So here it is. How do you define the flux density D? D is equal to D psi m, psi E, sorry. D psi E by dA. Units are coulomb per meter square. Flux crossing through unit area. So here it is. D psi E is equal to D dot dA. If you want to find out overall flux, what you need to do? You need to perform what is called a surface integral. Surface integral of D dot dA. Remember, there is no concept here. It's just what it is. It's purely a mathematical equation. What it is saying, if you know the flux density, if you want to find out the total flux, just perform the surface integral. That's all it is. Fine. Yes, it's purely a mathematical equation. Now I'll ask a very fundamental question here. Before that, always you need to convince yourself with the help of units. What are the units for D? Coulomb per meter square multiplied with the meter square. Here is a coulomb. Now I'll ask a very basic question. The question here is this the total flux which is crossing the surface? Is that the total flux? Or is it only the part of flux? I want answers from your side. Is that the total flux or part of flux? Come on, try to answer. Is this the total flux or part of flux? It is a part of flux, not total flux. Why? Because we have placed only the surface this side. But the flux is, suppose, let us say for the argument purpose, this charge distribution is creating some 1000 lines. But only 10 lines are crossing through this one. Yes or not? Suppose if you want to measure the total flux, what you need to do? You need to have a surface here also. Surface this side also. Front side also. Back side also. Top, bottom, left side, that side, this side. All the sides, there must be a surface. That means what kind of surface I should have? I should have what is called a closed surface. What kind of surface? Closed surface. Okay. That anyhow we're going to get in the Gauss law. Clear? Yes. Fine. Now let me turn the page here. Let us take what is called a Faraday's law. Faraday's experimental law. I'm going to turn the page here. Faraday's experimental law. Faraday's experimental law, according to the Faraday's experimental law, or intuitively also, you can feel that the flux will be proportional to the charge, isn't it? If there is a more charge, there will be a more number of lines. If the 1 microcoulomb is giving the 100 lines, 2 microcoulombs will give 200 lines, isn't it? So that is what the Faraday's experimental law is saying. What it is saying? The electric flux is proportional to the charge. The electric flux is proportional to the charge. If you increase the charge, number of lines crossing the surface increases. Clear? And further, what Faraday's experimental law says is not just proportional. The proportionality constant here is 1, according to the Faraday's experimental law. But here, total electric flux is equal to total charge. Total electric flux is equal to total charge. Yes, if you want to find out the total flux, let me go back. If you want to find out what is the total flux which is emanating from this charge, that itself is equal to the charge. Yes. So how you can write, for example, number one, what you can say, 1 microcoulomb of charge, 1 microcoulomb of charge will give 1 microcoulomb of flux. Number two, if it is a minus 1 microcoulomb, what will it will do? Minus charge will take the flux. Positive charge will give the flux. Okay. So you can write one more example as minus 1 microcoulomb of charge will take the flux, will take 1 microcoulomb of flux. So what is this Faraday's experimental law is saying, beta? If you want to find out the total charge, which is equal to total flux. If you want to find out total flux, which is equal to total charge. Yes, let me write down that law here. What it is saying? The total electric charge calculations are same as total electric flux calculations. So Faraday was purely a physicist. He was not a mathematician. Later, the Gauss has given the more sophisticated, more mathematical formulation of this Faraday's experimental law. Yes, that is Gauss law we're going to have later. The Gauss was a mathematician as well as he was a physicist. So he has given more sophisticated mathematical form for this one. And that is called as a Gauss law. Fine. So let me write down here what it is saying. The total electric flux calculations are same as total electric charge calculations. So this is a Faraday's experimental law. Clear, beta? Fine. Let us have one question related to this one. And after that, we'll go to what is called a Gauss law. Yes. I'm going to turn the page here. Here is a question. Find the amount of electric flux resulting from a non-uniform surface charge of surface charge density of 1 by x square plus y square plus 4 nanocoulomb per meter square, which is defined for defined for rho less than or equal to 2.5 meters, comma, z is equal to 5 meters. Okay. So rho less than or equal to 2.5 meters, comma, z is equal to 5 meters. Yes. Try this one. Find the amount of electric flux. What you need to do? You have to find out the electric flux resulting from the non-uniform surface charge density. It is 1 by x square plus y square plus 4 nanocoulomb per meter square, which is defined for this one. Surface charge is given for us. Is asking for total electric flux. What we know better from here? Faraday's experimental law. We know that total electric flux is equal to total charge. Simple law. But what kind of charge he has given? Surface charge. If the surface charge is given, how do you find out the total charge beta? By performing the surface integral. That's all it is. So the rest of the thing is mathematics. Clear? Yes. So you need to appropriately see here. The limits are given in the cylindrical coordinate system, but surface charge is given in the Cartesian. Better you convert that one into the cylindrical form. So then the mathematics would be simple. But before that, let me write down. Let me elaborate the limits here. What are the limits here? Come on, speak out. What are the limits, beta? Here the limits are rho is less than or equal to 2.5. Is it up to minus infinite? No. The lower limit for the rho is what is the lower limit for the rho? The lower limit for the rho is from 0 beta. So the rho is from 0 to 2.5 meters. And if he has not mentioned, you need to take the phi as a full limits. 0 to 2 pi. And what is z is equal to 5 meters. Okay, let us proceed further here. And how do you find out the differential area here? Here is a coordinate system. Rho comma phi comma z. Scaling factors are 1 comma rho comma 1. Differential A is equal to first two. Rho d phi z cap. Next two. Rho d phi dz rho cap plus dz d rho phi cap. What it is said here? Z is equal to 5 meters. What happens to the dz? Dz is equal to 0. That means these two terms will be equal to 0. So what is this dA? Rho d rho d phi z cap. So here it is dA is equal to rho d rho d phi, just a scalar quantity. So that is the differential area beta. But you need to convert that surface charge into the cylindrical form. Let me turn the page here. What is the surface charge he has given? Rho s is equal to 1 by x square plus y square plus, let me go back, how much is that? 4 nanocoulomb per meter square. Always remember, you need to cross check with the help of units here. What is this one? Its units are nanocoulomb per meter square multiplied with the meter square. So what you're going to get is the nanocoulombs. Come back here. We know, or we have, what we know? X is equal to rho cos phi. Y is equal to rho sin phi. X square plus y square is equal to rho square beta. So what is this rho s? 1 by rho square plus 4 nanocoulomb per meter square. So let us proceed here. So the total flux is equal to total charge, which is equal to surface integral of rho s. What is rho s? 1 by rho square plus 4 into dA. What is differential area? Rho d phi. Rho d phi. Separate out this one beta. Here it is rho divided by rho square plus 4 into d rho. Here it is d phi. Now what I'll do, I'll multiply and divide by 2 here. If I multiply and divide by 2, here the numerator is the differentiation of denominator. It is a standard integral. Yes. So what you're going to get here, it is a natural log of rho square plus 4. What is this rho range? Is 0 to 2.5. Here it is 5. Limits are from 0 to 2 pi. Substitute upper limit minus lower limit. 1 by 2 into natural log of 2.5 square plus 4 minus natural log of 0 square plus 4 into 2 pi. So here it is pi into natural log of 2.5 square plus 4 divided by 4. So the total electric flux is equal to total charge is equal to how much beta? Please check out this value. Use your calculator. Yes, how much is that? $2.95. Very good, very good. 2.95 nanocoulombs. 2.95 nanocoulombs is the answer. Okay, beta. Let me turn the page here. So that is all about the Faraday's experimental law. But let us see more sophisticated form for this one, which is given by what is called a Gauss law. Okay, let us try to have what is called a Gauss law beta. Observe here carefully. What is this Gauss law is? Let me write down the statement first here. The net electric flux coming out of any closed surface, out of any closed surface is equal to total charge enclosed by that surface. The net electric flux coming out of any closed surface is equal to total charge enclosed by that surface. There are only 2 points here need to be remembered. One is net electric flux. It is talking about net electric flux. The other one is a total charge. Net electric flux is equal to total charge enclosed. You should add one more word here. There are only 2 points. That is, if you write this one in terms of equation, net electric flux psi net is equal to charge enclosed clear. This is the thing. Let me explain this one with the help of a diagram, which is very convincing. Observe here. Let us consider the closed surface beta. Let us consider the closed surface. This is S0 surface. Okay. How can I convince that it is a closed one? It is something like a mango, closed one. Let me put some dots here. Why I'm putting these dots? I'm putting these dots to create the feel that it is a three-dimensional one. Clear? Yes. Now observe here carefully. Now let us consider inside this one, there are charges here. What are the charges? Q1, Q2, Q3, Q4, Qn. There are charges even outside here. Q1 dash, Q2 dash, Q3 dash, so on up to Qn dash. Clear, beta? Now let us consider this is a closed surface, something like a balloon or mango. On this one, there is an area, differential area, isn't it? Fine. So let me consider a small piece of area here. And what is the area of this one? dA. Clear? And what is the normal as it is a closed surface? The normal direction is always outwards, isn't it? There is no doubt in that. Because of these charges, the flux will be outside. or depending on the nature of the charges, the flux can be inside or outside. Yes. So the flux crossing through that small piece of area is called flux density beta. It is represented by the D. Units are coulomb per meter square. Clear? Okay, fine. So what it is saying here, what this Gauss law is saying, if you want to find out the net magnetic flux, you should consider only the charges which are inside, total charge enclosed, and you should discard the charges which are outside. Undoubtedly, each and every charge will have some associated electric flux, isn't it? If you have a charge, there is some flux lines around that one. Then why we are talking only, why this Gauss law is talking only about the enclosed charges? Why not charges which are outside? The reason being very simple. Suppose, let us say, if my charge is creating some 3 lines here, the charge which is outside is creating from 3 lines. 1, 2, 3. So if the charge is outside, what is happening? 3 lines are entering, 3 lines are leaving beta. If the charge is outside, 3 lines are entering, 3 lines are leaving. So what is the net? Net is 0. Because the charge is outside here, 3 entering, 3 leaving. But if the charge is inside, let us say this charge is creating some 4 lines. 1, 2, 3, 4. How many lines are leaving? 4 lines are leaving. How many lines are entering? No lines are entering. Isn't it? So 4 minus 0, there is some value. There is a net flow. No doubt each and every charge will be associated with some flux. But if you want to take the net flux, you should consider only the charges which are inside. And you should discard the charges which are outside. That is all the story is. Let me turn the page here. Before that, let me go back. Can I write this flux in terms of flux density beta? How this can be written? Surface integral of, we know that, d dot dA. I'm talking about the net. Net means what? I should consider the closed surface integral, which is equal to QENC. Means what? Charge enclosed. Clear? Yes. Let me show you with the example here. So what is the net electric flux come from the S0 surface? Net electric flux from the S0 surface is equal to, you can write like this, closed surface integral over S0 d dot dA, which is equal to charge ENC. That is nothing but a charge enclosed. What is the charge enclosed by the surface S0 beta? Is Q1 plus Q2 plus Q3, so on up to Qn. What is the net? I'll consider what I'll do. I'll consider one more surface beta here. I'll call it as a S1 surface. So what is the net flux? Net flux from the S1 surface? So the S1 surface is having the enclosed charges, Q charges as well as Q dash charges. Yes. So here it is. Net electric flux. S1 surface, which is equal to closed surface integral over S1 d dot dA, which is equal to charge ENC, which is having a Q charges as well as Q dash charges beta, isn't it? So here it is. Q1 plus Q2 plus Q3, so on up to Qn, plus Q1 dash plus Q2 dash up to Qn dash. Clear? So this example clearly illustrates the Gauss law. Clear, beta? Now what I'll do, this is a definition form we have. This is a definition form of Gauss law. Now we need to get the two more forms, which are called integral forms and differential forms. After that, we'll solve the numericals. Let me turn the page here. I'll going to define this Gauss law for the volume charge beta. Gauss law for volume charge. Rho V coulomb per meter cube. Okay, see here beta, what does that mean? Let us consider the closed surface here again. It is a closed surface. How can I convey that one? By putting a dots here. Inside this one, there is a charge. What kind of charge is this? This is a volume charge. Rho V, units are coulomb per meter cube. Okay. Inside this one, there is a volume. What is the volume? dV. On this one, there is an area. Okay. And here it is. Normal to this one is like this. N cap. And current crossing through. Sorry, not current. It is a, here it is differential area dA. Flux crossing through this unit area is a flux density D. Units are coulomb per meter square. Clear? Yes. Now what is this Gauss law is? Net electric flux. Coming out of any closed surface is equal to charge ENC, means what? Charge enclosed. So what is the net electric flux beta? Surface integral of D dot dA. Closed surface is equal to what kind of charge is there inside this one? What kind of charge is there? There is a volume charge. If the volume charge is there, how can you find out the total charge? By performing what is called a volume integral. Rho V into dV. So there is nothing new in this form. Just it is the other way of representation. So as you have noticed the integrals on both sides. There is a left side integral, there is a right side integral. As you have noticed the integrals on both sides, this is called a Gauss law. Gauss law in integral form beta. Clear? Yes. Now further, you can use what is called a divergence theorem. From divergence theorem, what you can write? From divergence theorem, what you can write? Closed surface integral of d dot dA is equal to volume integral of divergence of d into dv, which is also equal to, from here, volume integral of rho v into dv. Equate these two things better. Compare these two things. So what happens to this one? Divergence of d is equal to rho v beta. Array, this is one of the Maxwell equation. Isn't it? Very interesting. This is called Gauss law in point or a differential form. Gauss law in point or differential form. Clear, beta? Yes. See here, what they are conveying is the same thing. What is the meaning of divergence, which I have already explained? What is the meaning of divergence, which I have already explained? It is a net flow from the small piece of a box. Isn't it? So the net flow from the small piece of a box is equal to charge inside that. What is the charge inside the small piece of a box? Is a volume charge. What is this one? Net flow from the any arbitrary closed surface is equal to charge inside that. Is a volume charge. This is for any arbitrary closed surface. This is for the small piece of a box. Whether you are defining for the small piece of a box or whether you are defining for any arbitrary closed surface, the law remains same. Okay. So the three forms we have obtained here. This is a definition form, beta. And this is the integral form. And this one is a point form. Clear? Yes. Let us take some varieties of questions. Yes. It is divergence theorem. Let us take one question here. Three charges of 2 microcoulombs, 8 microcoulombs, minus 4 microcoulombs are at 4, 8, 3, 2, minus 2, 3, and 4, 0, 1. Respectively. Flux leaving the sphere of 6 meters radius with the center at origin is yes, what is the answer? Any answers? Let us try to understand here. Three charges here. 2 micro, 8 micro, minus 4 microcoulombs are here at these points. Respectively, flux leaving the sphere of radius 6 meters and centered at the origin is. Here is a sphere beta. Let us have some rough diagram. Here it is a sphere. How can I convince that is a sphere? By putting a dots here. And what is the radius of this one? 6 meters. There are three charges located here like this, somewhere here. We don't know their location. So it's asking what is the flux leaving this sphere? Sphere is a closed surface. So what is the flux leaving the any closed surface? According to the Gauss law, it is equal to charge enclosed by that, isn't it? So the net electric flux is equal to charge ENC, charge enclosed. So find out the location of them. If that location is less than 6, then the charge is inside. If it is outside, if it is greater than 6, that is outside. So what is the first charge? R1 is equal to square root of 4 square plus 8 square plus 3 square beta. Obviously, it is greater than 6. R2 is equal to square root of 2 square plus 2 square plus 3 square is less than 6 beta. R3. What is R3? Is square root of 4 square plus 0 square plus 1 square is less than 6. So the two charges are, you have to discard this charge which is outside. You need to incorporate these two charges. So what is the net electric flux? Is equal to the second charge and third charge. 8 microcoulombs minus 4 microcoulombs. Four microcoulombs is the answer. Then one can ask, if it is on the sphere, then what I should do? Valid question. Then if it is on the sphere, what you need to do better? Any answer? If it is on the sphere, what we need to do? How you need to take the charge? Because of the symmetry, half, someone answered. Very good. So some lines will be pointing like this. Some lines will be pointing like this. Just forget about this one. Half of the lines will be pointing inside. Okay. So if it is on the sphere, you need to take the half of that. Clear? Let us have one more question. I'm going to turn the page. If a line charge of density rho L is equal to, if a line charge of density rho L is equal to 15 nanocoulomb per meter exists at x is equal to 2 meters, comma, y is equal to 4 meters. For all z, calculate the net flux leaving the cube x comma y comma z ranging from 0 to minus pi to plus pi is. Yes, I'll give this one as a homework problem. Now let us spend on your doubts. Just raise your hand, I will come to you. Yes.
Hello, sir.
Equator.
Sir, if the charge is on surface, then all the flux lines that are entering will also leave the sphere. So, sir, the net should be 0.
If it is on the surface, huh?
Yes, sir.
Let me show you with the diagram. If the charge is like this, half of the charge is, it is assumed that half of the charge is outside and half of the charge is inside. Yes?
Yes.
So what
yes.
is the electric field lines here?
Inside.
What is the source for them? What is the source for them? It is
Half
charge
of the
which is
charge.
inside this part. This part. So only they are leaving. Nothing is entering.
Okay, sir. Understood. Thank you, sir.
Okay, but Pasha.
Good evening, sir.
Yes, sir.
Sir, in page number 105.
Why not?
One at seven, sir. 107.
107.
Yes, sir.
Ah.
Sir, in this question, he's given A value equal to 64.7 y cap minus 86 naught. Sir, if you're finding A value, we are getting that something is else, no, sir. 30 into.
How much you are getting?
30 into 3y minus 3z.
Are you
With the help
sure?
of that. Yes, sir.
He has not specified medium. Medium could be different. Who knows?
Sir, it may be surface, no, sir.
Huh?
If it's given as a uniform charge density, can we take as a line?
Yes, it is the line charge density.
Then it be kept in the formula rho L by 2 pi epsilon naught.
What I am saying here is, he has not mentioned it as a air. It could be some other medium. Epsilon is equal to some epsilon, not epsilon r.
Okay, I got it.
This was the previous ESC question. Engineering service.
Okay, sir. I thought that is not matching means it's
Okay,
option
okay.
B, C, D. That's it.
Okay, what you have done is correct, but that could be the other medium also, isn't it? That is not mentioned in the question.
Okay, sir. I got it. Thank you so much.
Your thinking is correct. Yes, any doubts?
Hello,
Yes.
sir.
Yes, better.
Sir, only ESC questions and note is enough for preparation, sir, because no need for a book for this time, means for less time, because more
If
syllabus
you
will
want
be
to
left.
follow book, you can follow this book, William Hythe book.
Actually, sir, I think this is means note is enough or not for solving only get problems. Note.
For solving, if you want to solve more number of questions, follow this book. I'll write it on the board. (2008) plus solved problems on electromagnetics by Syed Nasr.
Your maximum that is short type question, means up to
So many
20
questions are there here. Just to solve up to Maxwell's equations. And you no need to purchase this book. It is already available in the net.
Okay.
PDF is available. First, your preference should be for the previous Syed Nasr.
Thank you. Thank you.
Okay. Any more questions? Okay, then I'm going to close the session. Bye. Take care.
Good night, sir.
Good night.